Chapter 9, Part 8. We're going to reiterate the cross-bridge movement, which I tend to refer to as the cross-bridge cycle. So again, calcium was released from the sarcoplasmic reticulum and finds its way to troponin and binds with troponin, causing troponin to change shape, which in turn causes tropomyosin to change shape, which in turn reveals the active sites on actin. And of course, ATP is in here working hard as well. Step 2, cross-bridge formation. The myosin head is able to bind to the active site on actin and form the cross-bridge, and the phosphate is released from the myosin head. During the power stroke, energy stored in the myosin head is used to move the myosin head, causing the actin to slide past the myosin filament, basically pulling the actin towards the center of the sarcomere. ADP molecules are then released because ADP is what's left over from ATP once it was broken down into ADP and phosphate. Step 4, cross-bridge detachment or cross-bridge release will only happen if there's ATP present. So when ATP, the energy currency, binds to the myosin head, that causes the myosin head to detach or disconnect from the actin. Keep in mind that without ATP, when someone dies, that's what causes rigor mortis. So, when we die, we're no longer making ATP. And so if there is cross-bridge attachment, then ATP is needed to detach, and that's what causes the body to stiffen up a period of time after death, and we refer to that as rigor mortis because the lack of ATP available. So these connections after death will deteriorate, and eventually the rigor mortis will fade away. But if you've ever been curious about the physiological explanation of what causes rigor mortis, it's the lack of ATP allowing for cross-bridge detachment. All right, the next step. So ATP, back here on the step we just talked about, attaches to the myosin head, and that cocks it and orients it. And when the ATP is broken down into ADP and phosphate, or the hydrolysis of ATP, same thing, the myosin ATPase portion of the myosin heads will break it down into ADP and phosphate, which will remain attached to the myosin head, and that releases energy. During the recovery stroke, the heads of the myosin molecules return to their resting position, and it's kind of ready to go again. And then the whole cycle will start over again. All right, so summary of a muscle contraction. So this is everything in one screen. Everything from the events at the neuromuscular junction all the way to the cross-bridge cycle. So an action potential travels along the axon membrane to a neuromuscular junction. Voltage-gated calcium channels open. Calcium enters, forcing acetylcholine to be released into the synaptic cleft. Acetylcholine will attach to ligand-gated channels on the motor end plate over here. Where am I here? And allowing for those channels to open. Sodium will diffuse into the muscle fiber, initiating an action potential that travels along the sarcolemma and down into the T tubules. So here comes acetylcholine, causes these to open, and then allowing that propagation of an action potential to travel along the cell membrane down into the T tubules. There's some gates here that are not referenced here, but this causes a series of gates to open, allowing calcium to be released into the sarcoplasm. So action potentials in the T tubules causes opening of voltage-gated channels in the sarcoplasmic reticulum, which releases calcium. Calcium goes after troponin, which then will cause tropomyosin to move, because anything that binds or unbinds to a protein causes it to change shape. So when calcium binds to troponin, which is connected to tropomyosin, all of them move. That reveals the actin binding sites, allowing for, with the help of ATP, the myosin heads to attach, causing a cross bridge. Let's see, ATP molecules in the myosin heads are broken down into ADP and phosphate, which release energy needed to move the myosin head. The heads of the myosin myofilaments bend, causing a power stroke, causing the actin to slide past the myosin. As long as calcium is present, the cycle repeats. So that's everything that I have talked about in the last multiple slides in a nutshell. So during muscle relaxation, calcium will move back into the sarcoplasmic reticulum through active transport. And of course, active transport, as you know, requires energy. Calcium will move away from that troponin, tropomyosin complex, and a complex reestablishes its position and blocks the binding site. So this tropomyosin will re-block those actin binding sites. So we're going to stop here and pick up on part 9, I believe. I'm not sure where I am here now.